So yeah, I spent a lot of years doing physics, supercomputing at SLAC, the Stanford Linear Accelerator Center here. And that was fun. We learned a lot about scalability of code and how to deal with terabytes of data in memory, how to do linear algebra, and so on. Now, we're doing something else, and that's deep learning. Why deep learning, you ask? Or maybe you don't ask. Let's ask Google. The answer will be it's trending. And those of you who laugh, what do you think is the difference between causation and correlation? Right? I didn't do all of this, but I was there at the right time, I guess. So deep learning is a multi-stage system that does some nonlinear transformation at every stage. And you have some input, and you get some output at the end, and that's transformed multiple times with some nonlinearity in the middle. That's deep learning. Now, there's many forms of deep learning. There's many advanced forms. We are doing something that's more traditional, if you want. It's an artificial neural net, multi-layer, deep. It's kind of the same word, multi-layer or deep. It doesn't have to have just one hidden layer of neurons like the old neural nets, but you can have multiple layers of these hidden neurons. You see the little white dots in the middle there? These are the hidden neurons. So this would be an architecture with 4 and then 3 hidden neurons. And each of those 4 and 3 inside neurons will be connected to the outside. So on the left side, you have input coming in. That's the user feature space. And on the right side, you have the response space, which could be 1 number for a regression target, or it could be 10 numbers for like digit recognition. Okay? And the numbers in the middle, the little round balls, the white ones, the hidden neurons, they're not really numbers, but they're things that can make numbers if you want. They're these neurons that can get activated. And they're activated by the sum of incoming weights. And they're basically summing up not just the weight numbers, but how much they are activated as well. Like each previous neuron got some activation out, and that flows into the next layer with some weight. That's basically just a matrix vector multiplication, if you want, of the previous layer into the next layer. And once these neurons get that input, then they make a nonlinear transformation to turn it into their own output. So each little neuron sees a lot of inputs, sums it all up, and says, OK, I have a number 1249. Now I'm going to apply some nonlinearity to that and turn the 1249 to a 0.6. And that's my output. And then the next neuron gets a bunch of these 0.6s or something similar like that. So that's the idea. If you don't know what deep learning is, you should Google it quickly before we get to the next slide. Basically, it's a black box. It's hard to understand what's happening. You just understand the simple principle, right? It's not that hard. It's some numbers to propagate, whatever. You just have to figure out those numbers. So how do you find those numbers? Well, there's many schemes to do that. One of them is backpropagation that has been established as the very efficient one. You can do stochastic gradient descent. So you can have new training data coming in all the time. Each one makes a prediction, and then you see how good it is. If it's not quite right, you fix it. Just like boosting, you fix what's wrong. So in this case, you will take the mismatch with the actual response and say, feed that back to your network and tell every single neuron and every single weight in there what happened. And the neurons really don't care. It's mostly the weights that get changed. So all the weights get updated because you made one mistake. So it's a very expensive operation, right? One row comes in, you make a prediction, it's slightly wrong, you tell all the weights to change. And that's the power of math. This is a chain rule with derivatives and stuff. The chain rule propagates the error back into all the weights. And that update fixes the system to be better. And at the next row, it's already better. And then again and again and again. And we do this on like fast hardware, right? Today you have computers are cheap. You can buy good computers for little money, and it's worth doing it because you can get better accuracy out of your models. So the strength of deep learning definitely are the accuracy. It's the lowest bullet point there. World class at pattern recognition. There really is nothing better than deep learning at detecting patterns. And there's convolutional neural nets, which we don't have right now. Those are meant mostly to run on GPUs to do image recognition. That's one specific field. We don't target image recognition. We target the general case of simple structured data that has categoricals and numerical data, like real business data. A table can be 1,000 wide or more, can be tens of billions of rows. Anything in it, missing values, doesn't matter. The numbers can be ugly. They don't have to be standardized or anything. And we'll just take that as if we were a random forest model, and we'll spit out predictions using a deep learning approach. So that's the strength of H2O. It just works. It scales on a cluster. It has all the features that you need, regularization and so on. You can stop training at any time. You can continue. And it's just doing what you would expect a deep learning net to do. There's one extra thing that I want to mention is that the theory is not well understood, right? Deep learning, nobody really knows why it works or why it converges or whatever. Like there's some theory that says under some assumptions it's mostly okay and will converge to something reasonable, but there's no such one thing as a optimal solution. There's a lot, I mean, in theory, yes, but in practice, no. You don't find that. You'll only find some local minimum somewhere around where you started, basically. And that's why we have momentum terms to drive the search faster. So if I had to find the highest person in this room, right, and I would just have to like scan and like go and find somebody. And this is not that hard. It's only two-dimensional space if you want, because each one of you has an XY position. I could scan it brute force and I will find the highest person. But if you had a 100-dimensional space and you have to find the single one person that's the highest or the tallest, it's not going to be easy. So you just find the best you can do in a given amount of time. And deep learning has been shown to be very efficient at that. You just do brute force scan with this learning rate stuff that kind of dives through the space like a spaceship, and it turns around from time to time and finds something else to look into. And after a while, it'll find something that's pretty good. And your goal is to find something that's pretty good. Now, often it can be too good. It can overfit, and it can say, I found the perfect solution, in quotes, super great solution on the training data, but it's useless on the test data. So you have to add regularization, just like a logistic regression or so, to not overfit. And you can do that as well with deep learning. So the benefits here are that you can basically take any data set and you can run GBM or random forest or GLM or now deep learning the same way as always. We've had deep learning for a year or so, but now it's really part of this whole ecosystem, and it's just as fast now to train a model if you know how to tune the parameters a little bit. So you don't have to think that deep learning is slow. I can run a deep learning model that trains a few million samples per second, no problem. You just have to know that you're not using 1,000 neurons on each layer. You do like 20, 20, 20 or something, and it's going to be really fast. So another benefit is that you get a POJO model out. The deep learning model itself is exported as Java code, plain Java code. And you can look at that Java code, and you'll see a for loop, the matrix vector multiplication. You see the activation functions, the nonlinearities. You see all that stuff in the code, and you can learn how it works. That is the actual prediction that is being made right in front of your eyes. So that's a nice thing about H2O. All the models export themselves as plain code. And if you don't know how to do that, you can look in Flow. Every time you build a model at the bottom, it says, look at the POJO. And of course, all of this runs in Spark, in Python, in R, in like the web user interface, or through REST. You can just do a curl, and you can launch a job, and you can check the status later. Anything you ever do in R or Python is not going to run on that client laptop unless the server, H2O itself, is also on the laptop. But it doesn't have to be. Typically, the server itself runs on a cluster somewhere. It could be Amazon. It could be your own Hadoop cluster. It could be a Spark cluster. It could be a supercomputing cluster. It doesn't matter. As long as you can run Java, you're good, right? So that's the strength of this whole thing, is that it's very, very easy to run. It runs everywhere, and you get the same model out, whether you run it on your laptop or on a supercomputer. And I mentioned earlier this early stopping and the categorical handling and so on. There's all these benefits that we have added that is more than what it was in the 70s, if you want. But it's still kind of the same model. It's just now has support for Tweedy distribution or gamma distribution and so on. It's all together bundled up. So tomorrow at 11, at this stage, I'll talk about the top 10 deep learning tips and tricks, the deep dive, if you want, for those who've already used it, so that you know how to make the best of your time when you're trying to train a deep learning model, and how to navigate those waters. Because it still has the most parameters of any method, And you can easily get confused if you look at all of them and just do a brute force grid search over all possible combinations you can think of. It's going to take till the end of the universe, and your laptop will run out of batteries because there will be no power grid in a few thousand years from now either. All right, so all of you have installed H2O, right? Who has not yet installed H2O and is willing to just watch this show? That's fine. But I don't see anybody. That's great. So everybody now will actually do this with me. We'll run a little bit of deep learning here. And either R or Python, you can choose. We'll do a couple of things. So these slides are on the memory stick. If you want, you can follow these later again. But I won't go into too much detail what exactly we're going to look at. The goal is that we just do something in R now. So first of all, you have this directory here on the memory stick. H2O world. Let me make it even bigger. So there's this directory inside of H2O world 2015 training that's called tutorials. And in there, there's a deep learning directory. And outside, there's a data directory as well. So there's the data sets that we use. And actually, in this case, we're only going to use a very small data set, Spiral, which is 8 kilobytes. And if you look at it, it's just X, Y, and a color, black or red. And as the name suggests, it's going to be a spiral. So actually, who's going to do R here? Who's going to do Python? So R first, then Python. The other hand, yes, right. OK, perfect. So I'll show R first, but then I'll show Python as well. So what you would do here, you either go into the deep learning directory and just do r-f deep learning.r and say enter, and it'll just run everything. But then you have no idea what actually happened, and at the end you'll get a PDF file with the plots that were created for you. That's not bad. At least you can get something out of it, right? But most people would want to do this interactively. So either copy-paste it or something, or you do it in RStudio. So who has RStudio installed? Most of you? OK, great. So let's do that. I always do a kill all -9 Java because I'm paranoid that something else is already running. That's the one thing that can happen to you is you have too many H2Os everywhere, and then you start something and you don't understand what's happening. Usually that's the reason. So kill your Java processes, go into RStudio, open up this deep learning.rmd file, the one that's in here, in this tutorials directory, deep learning. So we're looking at this file now here. There's also this plain R version. There's a markdown version. There's an HTML version. So if you have nothing to do right now, you cannot run it, then you just look at the HTML file. You just open that, double-click on it, or type open deep learning.html in the Mac. It'll show you the whole output of the R session. So you can always see what's going on. So in RStudio, I'm going to skip the introductory text, and I'm going to load the H2O package with Control-Enter here. So this is an R Markdown file, and you might have to install the R Markdown package. If you don't do that, you should load the .r file itself, not the .rmd file. So I'm sure that you're familiar with running scripts in RStudio. If not, ask your neighbors. You just have to be able to execute cell by cell or line by line with Control-Enter, Enter, Enter. So we just loaded the library. Now we're going to start the cluster here. And I have a shortcut to run the whole cell at once. So not just the H2O init, but also the remove all. We just do a remove all to make sure that the cluster is empty, but we just started a fresh one, so it's all good. So is everybody at this point? Who is not at this point? Really? You're lying. Somebody is not at this point. All right. It's OK. Now you can do something like h2o.deeplearning, and you can ask the question mark or help or look at the arguments. You can run the example. So if I do this, it's going to run something on the iris data set. It's going to show all the help options here on the right. There's a lot of parameters. They're all explained here. It's not a lot of screen space, but it's good enough to see that there is at least a lot of parameters. Now, I typically only touch maybe 5 of them when I do my parameter searches, because everything else you can leave at default values and it will work just fine. Let's do this. So I'm saying defaults are fine. Let's do some fun stuff. So the fun stuff that we're going to do is this spiral thing that I showed earlier. We're actually going to look at that. And in order to do this, we'll have to define this function. So first I have to set the path in RStudio to point to this deep learning directory. So the file that you have might show something else there. I'm pointing it now to my H2 World memory stick copy. I put that into my home. And then I go all the way to the deep learning directory. That's the place where the script itself is. Okay? So point RStudio to that directory. Okay? Now you can do get working directory. And it will say, OK, here. Yours should look like this. It should point to the directory in which those files are, the .rmd files especially, or the all it really needs is the data directory outside. So that's why we go out with .. to the data directory on the next line. Oops. So this is all folded up here. See, it normally looks like this for you. So I'm going to load the spiral data set and then the grid data set. So the spiral itself is just the XY values with the color. And the grid data set is a Cartesian grid of X and Y's values at regular spaced intervals, 201 times 201. And later we'll use that to make predictions on these points and say, what's the color at this point? Is it red or is it black? And the models that we're going to build are going to be trained on the actual spiral data. Every one point that comes in says, I'm at this X, this Y, and I'm this color. And then the model has to predict what's the color at a given X, Y from this grid data set, where you have basically 200 by 200. So 40,000 questions are asked. What's the color here? What's the color here? What's the color here? What's the color here? And so on. And at the end, you'll have a map of predictions made by these models. And we can then plot them and see like where's the red, where's the black, and how it is separated from each other. That's the basic idea. So this R script here that I'm going to define now is purely there to do all this plotting of these contours. It doesn't look as pretty as the Python version that our great new member of the team, Kevin, here has implemented. And we'll soon show you the Python version as well. But for now, all we get is this complicated script, and then we're just going to launch it here. We're going to run this code. And I will make this window a little bigger here so that we can see something. And I trust you that you can still see the left side reasonably well. So right now it's building these models. Oh, it's already too big to plot, so let me make it a little smaller. So if you get into this stage where you can't plot it, you can just get out with Q and then run the cell again. RStudio is a little particular. If it doesn't fit, if the output of the plot doesn't fit, it's just going to complain and say, I can't fit this. Still doesn't work. OK, let's see. So who has been able to actually plot it? Some of you? Oh, great. What did you see? Did you see something like this? Yes? So this is what you're supposed to see. So deep learning learns the spiral. The contours are pretty nice. GBM, the gradient boosted method or gradient boosting machines, chops up the space with a greedy set of trees. Each tree is fixing up the errors of the previous trees. So it cuts up the space. And the same for the random forest, which you call distributed random forest, DRF. So they're both just approximating those smooth curves. But none of the methods, GLM is just a straight line because it is linear. So none of the methods actually gets the smooth spiral right other than deep learning. So you get some intuition what's this deep learning about, right? It somehow learns this contorted transformation. So now I'm going to run the next one. And that's actually going to, let me try it this way. Okay, now it's working. So this is now showing different architectures. Actually, I might have skipped some block up there. Let's go back up. I skipped the one with the checkpointing. The checkpointing actually says, first build a model with one epoch. And what is an epoch in deep learning? One epoch is one pass over the data. So in this case, one pass over the spiral data, then you learn the model. But you can iterate and show the same data again and again and again and again. And the deep learning model has a learning rate, so it's not learning that fast. It's like your baby at home. It doesn't learn everything immediately. You have to tell it again and again and again. And once you tell it 10,000 times, it'll say, okay, I got it. So that's the same thing here. So in this case, it took 750 passes over the data for it to finally get it. The first epoch, it said, sorry, it's just, this is the separation, just a straight line. So basically, it was still like a linear model. It was just a straight line. And then after 250 epochs, it got a rough idea, 500 got better, and so on. Does that make sense? Did you all get that? So then I showed you the other one just earlier by accident. I plotted this one first. This was the different architectures. So you can have 4 hidden layers, like 11, 13. I picked some prime numbers. Doesn't matter. It got an idea that there's some separation, but it wasn't really good. Then the 42, that number 3 times got it right somewhat. The 200 by 200 is the default. That's 2 layers of 200 neurons. So there's some nonlinearity because you have 2 of them, but not too much. And there's still a lot of resolution because you have 200 different neurons seeing every single XY value coming in. And each of those 200 neurons can make its own image, if you want, or each interpretation, its own interpretation of X and Y. So I have 200 neurons. Let's say you all are the neurons of the first layer, right? Each one of you will see my X and Y that I'm giving you. And you only look at the X and you only look at the Y and so on. And you look at the X times Y. And so you all have some idea what's going on between the two. And you then look at all the outputs of all of you again, right? And you're the second layer of 200 neurons. So imagine what you can do with this complex system that has the ability to see all kinds of numbers. And that's the 200 by 200 neural net. So it sounds like, oh, 200 is not that big a number, but actually it's pretty impressive what you can do with that. Even for big data, that works fairly well. And now you wonder, what's this nonlinearity about that I keep mentioning? The nonlinearity is actually, usually it's a sigmoid. Sigmoid is something goes from 0 to 1 softly. But there's a 10H, which is the same thing, which is the hyperbolic tangent, which goes from -1 to 1. It just scaled and shifted a little bit, rescaled in X and shifted and scaled in Y, but it's the same shape. That shape is fine. The problem with the 10H is it's never really 0 other than at 0 itself, which means there's always going to be some values flowing through the system from you to you. And all of you will be busy making the correction that came out of the answer to go back to these guys. Like every time there's something wrong, you guys will say, hey, you guys fix it this and this much, and that's too expensive. The rectifier will say, the different activation function rectifier, it will say, if it's less than 0, it's 0. It's the same thing to me. So as soon as you guys see less than 0, you just say it's 0, and you don't have to do anything. You're done. Next. You don't have to tell these guys at all. So that's the secret of the rectifier. It can shortcut stuff. And if you have enough of these straight lines, rectifier is just a straight line up. Once you're positive, your identity, 7 is 7, 12 is 12. It's not that nonlinear. It's actually still linear. But the fact that it chops off 1/2, that's the nonlinearity. And that's the cheapest way to do anything nonlinear. Just chop off stuff. It's almost like a random forest, right? Either it's left or right. And here you're doing the same thing, kind of. You can still shift the 0 around with some bias and with other input from the other layer. So if you can make some number, and you can say, all you guys added up, in the end it's 12. And then this guy on the other side will say, okay, 12 it is then. And if you guys decide that the output number should be -6, then the other side will say, okay, it's nothing then. So you all have the power to shift this 0 point around. And you can approximate any number, any function, I mean anything with this rectifier. So I think that was that. Just one thing here. The rectifier looks pretty bad, right? In the bottom right, the rectifier. Well, what's that extra thing? It's called with dropout. And that's the thing that was added in 2012 by Jeff Hinton, who's now at Google, and his people. The dropout is a way to make this network a little less smart, if you want. You just take some of these connections out. So some of you just don't talk to some of you anymore for this one example that I'm showing. So I'm giving you X and Y. You guys make a prediction, and you just drop it. You don't even tell the other guy. So how is this network now supposed to learn if you're not propagating information? Well, you're only not propagating some of it. By default, it's 50% you're keeping away. So this makes it faster because you don't have to do anything. You get nothing. You're not going to operate on it. And also on the way back, when you're fixing your errors, you're not telling the other guy because he didn't tell you in the first time, right? So it's basically just a sparse way of making the system a little less smart. And that's regularization. That will help you see the world, even though you're looking through like a net, a mosquito net or something, or somebody waving a hand in front of you. It's moving all the time, this non-zero and zero state. Like, it's not always the same guys that don't talk. It's all random, right? So in the end, you get a really nice, smooth vision of the world, if you want. And that's good enough to deal with regularization issues. So the generalization of these models is pretty good. In this case, actually not that great because it hasn't trained long enough. If you were to train this rectifier with dropout longer, it probably will be good. So you guys can try that. And also you can change the rectifier with dropout. That just means do a 50% default dropout. If you specify the hidden dropout ratios to be 0, then you get back the regular rectifier activation function. So they are just shortcuts for convenience. But you can just always use the rectifier with dropout and then turn down the hidden dropout ratios to 0. And that will then make everything like as generic as possible, because this rectifier with dropout is like the best activation function. It works pretty much in all cases. It's super fast. And you can always turn up the dropout or go down. So now we're basically done with this session. There's just one quick thing I want to show you is how to do this in Python. So I'm going to kill Java, and I'm going to say IPython notebook deeplearning.ipynb, and the same thing happens from here. So for those that haven't done it yet, or Jupyter, you can type Jupyter instead of IPython. The same thing will happen here. And now we're taking questions at this point. Yes, I think the microphone will come.
Where are the questions? So when you do the dropouts, are you doing a random draw for the dropouts, or is it algorithmic? Because I didn't get the same curve on as you did.
So the question is, the dropout, how is it determined? Who doesn't talk to whom for this one example of training data? So for every row that comes in, I determine randomly which row here doesn't talk to which column there or something. It's like the matrix gets cut, like some of the lines in the matrix get zeroed out, if you want. So it's not totally random. It's all of you in this row don't talk to, let's put it this way. I pick 50% of you, okay? And you just don't hear from them. That's how it is. But which ones it is fixed for one example at a time. The next example, it's different 50% of you. So all of you will send your output, but only to the other half that's left alive. So in matrix speak, that means all the weights that are there, half of the columns are zeroed out, or half of the rows. It doesn't matter how you see it. It's just, you have to just know what is what, or how it connects. But it's not a random pattern of the matrix that gets zeroed out. It's always full lines or full rows.
Hi, you talked about the weaknesses of deep learning earlier. Are there any problems for which it fails consistently, that it just shouldn't be used for those sorts of problems?
Yes, and I will address that tomorrow also in more depth. So for example, if you have 50,000 zip codes, okay, and that's one column, what zip code, and that zip code is encoded as a string, not a number. It's just an actual categorical factor. Those 50,000 factors will then get expanded into 50,000 extra neurons. So there will be input neurons, I call them, on the very left, not the hidden, not you, but the neurons that I give you, basically. So instead of X and Y, you will get 50,000 inputs that say, am I this zip code, yes or no? Am I this zip code, yes or no? This is called horizontalization or dummy expansion or one-hot encoding. It's all the same thing. It's basically making these categoricals into numbers, which is not very smart if you think about it. You have 50,000 new inputs, and most of you see 0 all the time, and only sometimes there's a 1 somewhere, and now you have to learn what that weight should be, right? And all the rest makes it slow, because the matrix from me to you is 50,000 times however many you are. That's the first input matrix, because every one of my 50,000 numbers is connected to every one of you. So if you have a lot of categoricals, it's not great. And there's ways to deal with that. And we have implemented some of these. And there's this new algorithm that does that explicitly, the dimensionality reduction. It's called GLRM. Okay.
Hi. I guess a deep learning newbie question. When we are setting up our deep learner, number of hidden layers, and I guess how do we set that up? Do we want a deep but short network, or maybe a little bit shallower but more neurons?
Yeah, that's the golden question, basically. If you can answer that, you're smarter than the rest of us. So I don't know. It's hard to say. So typically what you do is you do 2 layers or something. If you do only 1 layer, you feel like it's not fair. It doesn't have a chance to actually learn something nonlinear. It's still a little bit nonlinear, but I would do 2 layers at least. I wouldn't go beyond 5 layers typically, because it gets slow. So I would do 30, 30, 30, 30 or something. Try that. Maybe then do a 60 by 60 or 100 by 100, or maybe 3 times 200 if you have more time to run. Some of the best models I've ever built were 600, 600, 600, 600, 600, right? But the benefit you get from doing 600 versus 200 is not that much. And 200 is going to run, it's quadratically faster, right? Because it's 200, every one of you talks to every one of you. So 200 by 200 is a matrix there. If yours was 600 by 600, it would be much bigger. So you have to pay the price in time. And what is it worth to you to get a better model?
Thanks.
Yeah, I wanted to ask about initialization of the network. Do you have any, is it just completely random, or do you have any smarts to it?
Sorry, I couldn't.
How do you initialize the weights?
Yes, so the initialization is done randomly, but not totally randomly. So the uniform random distribution has a scale, right? How much? Not 0 to 1, it's 0 to something. And that biggest number range, if you want, that's given by the size of the 2 layers connected by those weights. So my input layer and your hidden layer are connected by us, the weights, right? Every X and Y goes to every one of you. So the values of those 2 times you, your 200, those 400 numbers, those are given by the fact that you are 200 and I am 2. So there's a formula that computes how big the amplitude should be. And if it was 500 times 500, then the amplitude would be a little less, because you have more contributions adding up. So it's an automatic smart determination of that initialization. And the learning rate, by the way, is also adaptive. So you don't have to worry about any of that. No manual tuning necessary. You can literally say go, and it will just find a good solution for you. And pretty much all the time.
Following up that question before about number of intermediate neurons, do you change it based on number of input neurons? And does it change, by, like, as it flow? Do you want more neuron up front and then smaller layer later, or
It depends. The question is, of course, how do you know where should the work go into making those nonlinear features, right? So if you have a very complicated input, then you might want to give more neurons to read that input. But if you have maybe simple input, let's say 10 numbers, but you want to predict which of the 10,000 classes that belongs to, then maybe you need more neurons in the end to be able to then, from those neurons, determine the 10,000 classes. So you kind of have to know where the complexity is of the thing. You can't just say make it like a sausage that's 50, 50, 50, 50, might not be the smart thing. So it's really where do you want your complexity to be, right? Do you want more resolution or do you want more nonlinearity? Do you want to be able to distinguish the classes better at the end, the output classes? Or do you want to just see sharper? If you want to see sharper, you make more neurons. If you want to be more nonlinear, you make more layers. If you want to have better separability of the classes, you want to have more neurons at the end. So for the MNIST example, we had 1,000, then another 1,000, then 2,000, just to be able to get those 10 classes better at the end.
All right, last question. I was wondering if you could offer any thoughts on approaches to regression problems with multi-dimensional outputs.
Sorry, you're saying multi-target regression? Where is it? Oh, here. Okay.
So, for instance, numerical regressions with, say, 2-column outputs and some approaches to those?
Yes, so we currently do not implement that. If you have 2 outputs, you would have to build 2 models.
And you think that's a reasonable approach? Or do you have any suggestions on approaches that we might be able to take for those sorts of problems?
Yeah, you would have to do something hierarchical where you first predict something with one model, and then based on that extra predictor or something, you predict another's target, and hope that's good enough. But you can't reuse the same features that were learned to make one output layer, and then later you make a different output layer for the other target. So you would have to retrain two models. They would all have to train all of the features. You could argue that each model is better at doing this one target than having the neurons to be constrained to learn both targets at once, right? Maybe the features don't really work together, but sometimes the features work together, and then you would be better off building one set of neurons that just learns both things at once. But yeah, we don't have experiments doing that because the frameworks right now supports one output only. So one target, which could be a regression target, a number, or it could be a categorical factor, then we'll do classification. And also, by the way, when you run deep learning on a number output, like the response is a number from 0 to 9, let's say, that's not going to do MNIST classification yet, because 0 to 9 is a number, and it will treat it as a regression problem. You need to do as factor, or convert it to a factor in Python as well. R or Python, you have to explicitly convert the output to a factor to then make it a classification problem. Otherwise, it will just do a regression. But if it's already strings, then it's of course fine. Or if it knows it's categoricals, it's going to handle it right. But if it's numbers, H2O doesn't know that you want to do classification. So that's one thing to keep in mind. It's the user's responsibility to set the target, the response type, column type, to be a factor if you want to do classification. Okay? Thank you very much for your attention. And tomorrow, there's more time. Actually, even today, at a later stage, I think almost close to 6 or so, 5 something, is going to be another deep learning presentation on the other side. So if you want to come over and ask more questions, you're welcome. Thank you.